Using software is a lot of fun. I can click a few buttons, and this happens. Do you know how hard that would have been a few decades ago? I mean, sure, we are currently failing a completely preventable pandemic and setting fire to the only planet capable of sustaining human life, but look at these! Woo! Yeah! Wahoo! Where were we? Right, using software is fun. But you know what's even more fun? Modifying software. And I'm not talking about modifying its source code and recompiling it. That's something for the Free Software Foundation, founded by Hatsune Miku in 1985, to worry about. Modifying source code would be too easy. The hard part is getting it to build again. We're not going to bother with either. Instead, we are going to try and change the behavior of a program in its compiled form. I do believe this technically counts as hacking, in its more general sense, like messing around with something. Not in a nefarious sense, like I'm hacking onto the bank servers. Oh god, am I on a list now? Well, can't make any 30 under 30 lists anymore, so I'll take what lists I can get. Before we start modifying programs, we must first understand what a program is. And there's a lot to say about this, so I'm going to simplify and hand wave through a lot of things, not because I think you can't handle it, but because I'm trying to keep this video short. A program is like a recipe, as in it's a list of instructions to follow to make something happen. Just like a recipe, you need to follow the instructions in order. And just like a recipe, there's prerequisites or dependencies. A crumble recipe will specify that you need sugar, flour, butter, and some sort of fruit. Likewise, a program that generates spectrograms for music will say, I need to be able to decode compressed audio files and write images probably, maybe even open windows. But a program is a recipe for computers, not for humans. I mean, technically, humans wrote their own recipe, which is the source code, and then they asked the compiler to translate it into a recipe for computers, which gives assembly and then machine code. And machine code is the thing that's in exe files, for example. What's in those files is almost ready to execute. When you start a program, the file is mapped in memory, and then some light processing is done, and then boom, it's ready to be executed by the computer. And by execute, I don't mean to put to death. I mean to interpret a series of instructions. That's right. A CPU is an interpreter. Fight me. And although that's actually very, very far from the truth, for the purposes of this video, we will assume that the computer is just a dumb machine that just interprets instructions one at a time, one after another. And that's not true because the computer is trying to be fast. And so in actuality, it's doing a bunch of work in advance and some things in parallel, but it's trying very, very, very hard to pretend that it's simply doing things in order. So we'll just believe the lie for the time being. The most interesting things a program can do is compute stuff and access a computer's resources. A program may add numbers together, for example, to check if a number is larger than another number. And depending on that, it may decide to write a value to one place or another. And there are two main places a program may write to or read from. There's registers and memory. Registers are really fast, and you have to use them when you want to add numbers or compare them, for example. But you also have a very limited amount of them. For everything else, there's main memory. Registers have names, and nowadays they're usually 64-bit wide, which means you can store 18 quintillion different values in them. There are bigger registers as well for floating point and SIMD operations, but we don't need to worry about them. As for memory, we can think of it as an enormous book that any program can read and write from. Again, that's mostly a lie because virtual memory is a thing and you can map files and devices into memory. But again, that won't come up in this video. Or will it? And with just that, we can make this happen. Woo! Computers! Now we've got sort of a high-level theoretical view of how programs work, and it's time to make one ourselves in Rust. Because I said so. My video, my rules. And we'll do this on Linux because why not? So I've already got Rust installed here and it comes with cargo. So if I just do cargo new, it'll make a new program for me that just prints hello world. That main.rs file is the recipe for humans, and you can tell because it's mostly English words rather than hexadecimal nonsense. Then if I do cargo run from the right directory, it should print something. Yay! Now, I said some translation needed to happen, and it did, but it was all handled transparently by cargo. If you look inside the target directory, you can see there's a debug directory, and in there is our executable. If we ask the file utility what kind of file it is, it confirms what I just said. It's an ELF. I mean, it's an ELF file, which stands for executable and linkable format. And now comes the fun part. Should we look inside? I think we should. We can't use a text editor for this because it's not really text. Instead, we'll use Hexel, a hexadecimal viewer for the terminal that has pretty colors. There he is. It even says ELF right there in the file. Now, I can't tell you much else just by looking at that screen because I am not a beep boop machine myself, contrary to popular belief. But if we use a tool like readelf, which decodes ELF files, we can see it's divided into different sections. There's debug stuff, some text. None of this is instructions though. It's not adding numbers or comparing them or accessing memory. It's just how the program's file is organized. Now we can list symbols with nm, and that's more interesting because all our functions are in there. Well, we only have one, and its name is mangled. If we want to show instructions, we need to disassemble the program to go from machine code back to assembly. And we can do that with opsdump. And because we don't hate ourselves, we'll use Intel syntax. We'll disassemble just the main function, and that is assembly. Now, depending on what your background is, this may range from completely mundane to super scary. But be not afraid. As promised, most of what's happening here is just messing with numbers and memory. Oh, and also calling functions. Now, you can think of functions as recipes, too. Sometimes a recipe will say you need sliced apples, and you can think of it as a function whose input is whole apples and whose output is sliced apples. So really a program is more like a library of recipes with an entry point, like a recipe we start with, and that might send us on a wild goose chase doing all kinds of other recipes. If we look at the instructions we have here, we have sub, which is for subtraction, not for bottoms. We subtract 0x38, 56, which is 7 times 8 or 7 times 64 bits from the RSP register. And then we have LEA, which stands for load effective address, and is used for both memory stuff and some calculations. Here, it just copies something from memory into the RDI register. Later on, we have a move, which copies a constant value, 0x1, into the EDX register. And then we have XOR, which stands for exclusive OR. Here it's just used to set the value of the EAX register to 0 because it's shorter to use XOR than a move for that. You can see the move above takes 5 bytes to encode, but the XOR is just 2 bytes. And finally, we have a couple call instructions, which call functions, and then ret, which returns. Okay then, now that you know everything there is to know about assembly, let's move on to crime. Okay, maybe you don't know everything about assembly just from this video, but you know almost enough to be dangerous. For example, if we open the file in a hex editor and we search for the machine code that is started the main function, 4883EC3848AD7C24, and we replace the first byte with C3 so that instead of a sub, it's a ret, and we'll run the executable again, it prints nothing because now our main function returns immediately. And just like that, we have become hacker. And I don't know about you, but I kind of have a taste for it now. I want more. Much, much more. Well, first of all, I don't ever want to enter that dreadful hex editor again. Do you know how long I looked for a simple hex editor I could use from the terminal? You don't want to know. And no, vim plus xxd didn't work for me, it just kept corrupting the file. Anyway, I simply don't have the time to change bytes by hand in an executable, however fun it might be. I want a program to do it. To itself. We're gonna need 2 functions, hang on. There, we have 2 functions, and one of them says hi, and we can verify that it's still in the executable with nm, and it is, and we can disassemble it, and it looks very similar to what main was before. We've got all the classics here. We've got sub, LEA, move, XOR, call, add, and ret. Have you noticed that the sub RSP 0x38 on top is later on done by an add RSP 0x38? That's because that's how you allocate and deallocate memory on the stack. You just change the value of the stack pointer and boom!
Free real estate.
And that also explains the little RSP plus 0x8 we see used in LEA. That designates a location relative to the top of the stack. We also have RIP relative addressing going on, which we don't need to worry about for now. So, modifying our program from itself. How do we do that? Well, first we'll need the address of say hi. Now, Rust has both const and mute pointers, and since we're planning on writing to it, we'll need to make it a mute. The as operator here is used to cast between a function type to our pointer type, and the star operator dereferences the attr pointer, and that is wildly unsafe because the pointer could point to anything, so we need to do that inside of an unsafe block, which is Rust for I accept the consequences. Well, that was easy. So let's run it, and a segmentation fault. Well, I guess we won't be doing any more hacking today. Cancel the video. No, wait. That's just memory protection. See, different parts of the program, when they're mapped in memory, are protected differently. The instructions in the .text section have R+X protection. They're readable and executable. We can actually check that if we start our process paused using a debugger. Then with info proc, we can get a numeric identifier for our process, and in the proc directory, under the directory for our process, we should have a maps file, and there. It shows all memory mapped files for the process. It starts with our own executable file, and you can see most of them are read-only, and only one is executable. That's where the machine code is that we are trying to change. So, are we stuck? Well, no. This is Linux. We can do whatever the heck we want. We just need to ask nicely to remove the protection. And we could do that with the region crate. So we'll just call cargo add, and now we can call protect with handle. Now, why with handle? Well, that version gives us a guard that, when dropped, will restore the previous protection. And that seems like a good idea before we go on and call say hi. So we just keep our guard in the scope, write to memory, and let the guard fall out of scope, which should restore the previous protection. Okay, let's give it a shot. More segfolds. Ooh, okay. Here's the thing. We can't actually change the protection for a single byte. We can only do so for a memory page. And the problem is, the code for the main function and the code for the say hi function are on the same page. So the second our protect call returns, all our code stops being executable. And because our computer is masquerading as a simple beep boop machine that executes things in order, it tries to execute the next instructions and goes, wait, what? And kabooms. That's a theory, because to be fair, we are witnessing the exact same thing as before. For all we know, calling protect didn't do a damn thing. But if I'm right, and I am, all we need to do is to change that read-write to read-write execute, and everything should work. But before we do, I'd like to verify my theory. It's not particularly hard. I mean, first let's add a couple print statements and run it again. Okay, first one prints, good. Let's run it again, but under strace, asking it to look for the mprotect system call. What's a system call? It's like a function call, but to the system. I really don't want to spend too long on this. There's protection rings, and the operating system, in this case Linux, runs in ring 0, and our program runs in ring 3. And because all this runs in a VM, there's even a ring -1. Fun, right? So basically, memory protection is a feature of the operating system. So we need to call from ring 3 into ring 0, and that's a system call, or just syscall. All right, let's see. There, disaster, as planned. We see a bunch of unrelated mprotect calls, then our print statement, and then our mprotect call, which immediately causes a segmentation fault, which shows up as sigsegv, signal segmentation violation. And we could have reached the same conclusion by simply using GDB, but I really wanted to show off strace. So now that we've validated our theory, let's try and apply the fix. We'll change read-write to read-write execute and run it, and it prints nothing. Nothing at all, which is exactly what we wanted. But this is easy mode, because we control everything. The program we're modifying is also the program we've written ourselves, and so we could just as easily change the source of say hi instead. It would be a lot more fun if we could modify the behavior of another program. And the easiest way to do that on Linux is to use ld preload. ld preload is an environment variable that is read by the dynamic linker or dynamic loader when it starts up a program. If you set it to the path of a dynamic library, or in Linux parlance, a shared object, it'll load it into the program. So let's first turn our crate into a library, which we can do by adding a lib section in cargo.toml, under which we'll have crate type set to cdylib for C dynamic library. And now that our crate is a library, we'll want to rename main.rs to lib.rs and then build it again. And now we have a dynamic library. Let's ask the file utility what it thinks about it. And yep, it's a shared object. Now we can preload it into, say, cat, which is command line utility that we can use to print the contents of a file. If we run it without ld preload, it shows this. And if we run it with ld preload set to the path of our shared object, it shows the same thing. I don't think the main function is being run, which would make sense because it's no longer an executable, it's just a library. So we don't even know if it's actually being loaded. Luckily, there's a way to find out. If we also export ld debug to say files, we can see what actually gets loaded. Yep, our library is the first thing being loaded. Now we just need to be able to run some code when the library is loaded. But libraries have no entry points. We can't just name a function main and boom, we have an entry point. Luckily, libraries can have constructors. It's not dark magic, it just adds an entry to one of the ELF sections we saw earlier. But it's a bit annoying to set up, so we'll just use a crate that takes care of everything for us, the CTOR crate. We'll have our constructors just say hello from Rust, so we know it's been injected properly. And if we run cat again with ld preload set, we see hello from Rust. Well, hello to you too. So, we're in cat's address space. From the 2 we have at home, I can tell you it's cute for now, but it probably doesn't end well. In the meantime, what can we do with it? Well, cat prints the contents of a file, and it's written in C, so it probably calls the open function from libc. Maybe we could try and hack that. First, we'll need the address of open, and there's a couple of ways to do it, but I guess because our library also links against the C library, which we can check by just running LDD, we can just declare an extern function. And again, we can cast that to a const u8 and print it out. Yeah, this looks reasonable. At the very least, it's not 0. And now, same modus operandi. We unprotect, we patch, and we reprotect. As before, we'll just overwrite the first instruction of open with a ret, which should return immediately. It's showtime. Let's run it, and it gets stuck. Well, it appears stuck, but it didn't segfault, that's a start. We can also easily control C out of it, which sends SIGINT, the interrupt signal, and it exits gracefully. So what could be happening there? This is not movie magic, by the way. I was actually stuck on this when I wrote the script for this video. Yes, there is a script. There is always a script. But when messing around with it, I found something interesting. If we try typing something and pressing enter, it repeats the output. And if we press Ctrl D, which closes the standard input file, it exits gracefully too. So cat is reading from stdin exactly as if we'd called cat with no arguments at all. And this is fantastic. Because I was struggling to find a way to talk about calling conventions, and it just came to us. See, the open function from libc returns an integer. That's just a number. I promised computers were mostly messing with numbers in memory, and that number corresponds to a file descriptor that we just opened. If it returns a negative number, it means the operation failed, but anything 0 or higher is just a file descriptor, a number that describes an open file. And the way functions return values on x86-64 is through the rax register. So, what happens if we return from the open function without changing the value of rax? It thinks the return value of the function call is whatever happened to be in rax at the time. And in that case, because we're seeing what we type being echoed by cat, it happened to be 0. Every process has at least 3 open file descriptors to start it. Those are 0 for stdin, 1 for stdout, and 2 for stder. And I've tried to verify that by running it in GDB. It's a bit tricky to preload our library in GDB, but we can do it easily by using --args and using the env utility, which is a little wrapper that allows setting environment variables. It's perfect. If we just run it, we observe the same behavior. That's good. I mean, sometimes bugs disappear under the microscope, inside the debugger, and those are called Heisen bugs. Now, let's just set a breakpoint on open and run it again. Okay, we've reached open. Let's use step E to step through instructions, and wait, this is the actual implementation of open. This is a Heisen bug after all. But hey, this is a faster than Lime video. Of course I'm gonna have a theory. Or rather, I have a question for you, the viewer. How do you think GDB sets breakpoints? Now, in case the demonstration wasn't clear enough, a breakpoint is a place in the code where we ask the debugger to stop execution so that we can inspect the state of the program. Now, you've seen me step through the program instruction by instruction before, so surely there's a facility to do that. But that also sounds like it might slow down the program a lot. It does. So surely debuggers have another way to stop program execution at a given point. They hack the matrix, they patch the function. They just override it with, say, a trap instruction, or int3, which is 0xcc in machine code. And then, because they control the process being debugged, the inferior, they can catch that trap instruction and let you examine the state of the program. But how does continue work then? Well, by simply restoring the original code of the function on there. And you know the problem with that? It's apparently restoring from the file, or at the very least, its own copy of libc.so, which provides open. So by setting a breakpoint on open, we undid our hack. GDB overrode it with int3, and later on restored the original code for open. And we can verify that by disassembling open right after we've patched it. We see the ret as the first instruction, and right after we've hit the breakpoint, we see the original code, which is an endbr64. Destruction time. Does that mean we can manually trigger a breakpoint by writing an int3 ourselves? Let's find out. We'll just change the 0xC3 to 0xCC, and running it manually exits with trace trap. Very well. Now let's load it in GDB, run it, and yep, it catches the trap and acts as if we'd set a breakpoint there. The problem here is, because it's not a breakpoint GDB set itself, nobody's going to restore the original code instead of the int3. Luckily, NBR64 is actually a repz followed by a nope, and repz is encoded as a single byte. So we've effectively just ruined indirect branch tracking, but not broken the program completely. By the way, that's not just any nope. It's a nope on register EDX. I love how x86 is just like, sir? A nope, certainly, sir. And on which register will you want to be noping today? EDX. Excellent choice. But it's a clever trick, because there's so many ways to spell nope, which is no up, and it's just ignored by the CPU. It's used here to indicate something to newer CPUs, without it breaking for old CPUs. It's graceful degradation, just like in the web. Okay, let's make that cat fail. We'll just write -1 into racks. And, okay, actually I have no idea what the machine code for that is. But no worries, we'll just use an assembler for that. I mean, we could use NASM, but let's use YASM, the BSD flavored rewrite, because I've never used it and I'm curious. So we'll make an ASM file, define a fail symbol, and just move -1 to the racks register and return. And assemble it by calling yasm-f elf64 fail asm, and it'll produce a fail.o file. nm, which by the way stands for name list, shows a single unnamed symbol. Okay, just use objdump on there, still with Intel syntax, and there's our machine code. It's quite a bit longer than just a ret, so we'll have to make it a slice. Inside our unsafe block, we'll make another mutable slice that will represent the destination where we're copying the code, and we'll call copy from slice on the destination slice with our machine code as an argument. And if we did our job correctly, nothing should work anymore. I wonder what cat prints when open fails. Bad address. Lol. Lemao. Okay, buddy. Oh, I guess that's what happens when you return a negative value without setting the no variable. It too is set to whatever the last error was, I guess. Well, I think we've all had our fun, so it's about time to close up this video. What's that? You want more? Okay, how about we have cat read from a completely different file instead? It can't be that hard. We don't even have to change much. We can just open a file in our constructor, retrieve its file descriptor, and make open return that value all the time. Now, opening a file is as easy as file open, and we can get the file descriptor with as rawfd from the as rawfd trait, which is implemented for stdfs file. Now, our code can't be static anymore, right? The file descriptor returned there could be anything. So we have to mess with that machine code Yasm gave us earlier. But you know, I'm looking at it and I'm seeing 48C7C0 followed by fa. And to me, it seems like 48C7C0 is really the move a constant to racks part, and fa is the constant itself, which as a signed 32-bit integer, look at us getting technical all of a sudden, would be -1. So if we just overwrite that with a value of fd, it should work. So okay, instead of having the whole code as a single slice, let's build it up as a vec. First we'll have 48C7C0, and then our file descriptor as little endian, because that's what the CPU expects, and then C3 to return. Now, is there a better way to write this? Almost certainly. Am I going to bother? Hell no, this is bonus contents. We can have a little heap allocation as a treat. Very well. Time to test our crimes. Do they work? They do not. Bad file descriptor, huh? Why in the world would it have... Ooh, it's because RAII. Resource allocation is initialization. Once we hold a file, we know it corresponds to a valid open file descriptor. But also, when we let it fall out of scope, it closes the file descriptor. So I guess it's more like Arctic. Resource destruction is cleanup. Damn Rust safety getting in the way. Don't worry though, there's a way around it. I mean, we're already removing protections and overriding code. What's one more crime? Rust values, much like citizens of the European Union, have a right to be forgotten. That way, it won't actually run its drop implementation, its destructor, if you will, when it falls out of scope. So just a quick std mem forget, and aha! It works! Hacking is so fun. Are we having fun? We are, aren't we? It would be a shame if the video were to end suddenly.
Freuder schöner Götterfunken, Tortel aus Elysium. Wir betreten feuertrunken, himmlische dein Heiligtum. Deine Zauber bieten wieder, was die Mode streng geteilt. Alle Menschen werden Brüder, wo dein sanfter Flügel weilt.